Welcome back to another lecture of design of concrete structures. Uh, Today, we are going to discuss about the losses in prestressed concrete. We have seen the previous chapters, we have lectures, we have seen the concepts of prestressed concrete and how to find out the upper and lower stresses of prestressed concrete in a beam. What the different cases we have seen, some 6 cases we have seen with tendons with the different profiles. So in this lecture, we will be touching on important aspects of prestressed concrete, which is the losses in the pre-stress. So it's an important portion in the pre-stressed concrete, and the main design part of the pre-stressed concrete. This loss of pre-stress has got a very important role in that. So with these losses we need to assess while designing the pre-stressed concrete, and we'll be doing some numerical problems also to get familiar with how to calculate the losses. So in short, what's happening is we have seen the pre-stressing. There is an initial pre-stress in the steel. Let us say we are using the tendons having stresses 1500 to 2000 Newton per millimeter square, and once it is stressed and the concrete is cast, and when we cut the steels, we are supposed to get experience the same stresses actually, but normally it doesn't happen. We will be having a loss in the order of 200 to 230 Newton per millimeter square, because of which we use high stressed steels actually. Otherwise we could have gone for let us say Fe415 and all we don't use actually. We will use the steel in the order of 1500 to 2000. So these losses plays an important role. So in general the losses are in two types. One is immediate loss in the sense once it is stressed and released, suddenly it happens at that point of time, that context, that is called immediate losses. And the time dependent means over a course of time, as the time progresses, there can be some another losses. These are the main two category. I'll just touch upon. We will go in detail each one by one. And generally the immediate losses are: one is elastic shortening of the concrete, elastic deformation of the concrete. I will see what it is. So this will happen especially mainly in pre-tensioned and the pre-tensioning, and the post-tensioning. If all the tendons are pulling at the same time, stressing at the same time, it will not happen. But if you are stressing it successively, it will happen. We will see how it is. And another thing is a frictional loss due to friction and wobble effect. It is for the post-tension beams, post-tension, not in pre-tensioning. Another, this is the losses due to anchorage slip or wedges, slip due to the wedges actually. It is also happening only in the post-tension beams. And the time dependent losses means over a course of time, the losses happening. It is mainly 3 types, and the thing is that this will happen for both, irrespective of what mode you are doing it. It will happen for pre-tensioning and post-tensioning also. So those loss due to creep, loss due to shrinkage, and relaxation stresses. Yeah, loss due to relaxation stresses. So this we will see one by one. Yeah. So mainly some 6 types. Immediate losses are 3 types. Another time dependent losses are 3 types. Time dependent losses happens for both pre and post tension, whereas this immediate losses, it happens mainly post tensioning, and elastic shortening, it happens for pre tensioning. Yeah, let us see one by one. Let us discuss the losses due to elastic deformation or elastic shortening. So it's an immediate loss. So think a case wherein the steel tendons are stressed, okay, and concrete is cast, and we cut the tendon. So what will happen is these tendons will try to come straight. It will try to push the concrete both sides. Yeah, but concrete being very strong in compression, it will not allow. But there is a small chance of the concrete will also undergo some compression. So that is called elastic shortening. So because of which there is a loss in the stress. So that is called loss due to elastic deformation. Okay. So what is that? It is the steel will try to push it. So at the same time, concrete will also shorten. It will also undergo a deformation, shortening, very small actually, but still it will create a loss in the stresses of the steel. That's called losses due to elastic deformation, elastic shortening. So it is this is how we calculate loss is equal to M into Fc, where M is nothing but a modular ratio, which ratio it is, which you would have studied actually. It is nothing but Young's modulus of steel divided by the ratio of Young's modulus of steel and Young's modulus of concrete. And Fc is the stress in the concrete at the level of steel. Okay, that is important actually. If I take this section, then if I take this section, for example, okay, then at this level of steel, what is the stress in the concrete? That is what important. So similarly, suppose I take this section, end section, then at this level of this steel, what is the stress in the concrete? That is Fc. So we will see how to calculate when we do a problem. So this is basic understanding. Okay, modular ratio of is nothing but Es by Ec. So the question is, when you find out the stresses in Fc, which portions, which section we will find out, because this loss will happen for the complete session. Okay, so which section we will find it out? So the answer is very simple. Like we will take the average stress. Suppose the tendon is in a bent up tendon like this. So let us say this section the stress is F1 and this section the stress in concrete is F2. Then the average stress is nothing but you can take F1 plus F2 by 2. Okay, F1 plus F2 by 2. Alright. Whereas in case of a parabolic tendon, let us say at section 1 stress is F1 and section 2 the stress is F2. Means when I say stress means stress in the concrete at the level of steel, F1 and F2. Then the average stress is F2 plus 2 by 3 into F1 plus 2. Why? Because this is a parabolic profile, this is a straight profile, linear profile. So linear profile we can take average F1 by F2, but on parabolic profile we cannot take. So parabolic profile we will take the average stress like this only, F2 plus 2 by 3 into F1 plus F2. Yeah. So this is an important point, important takeaway. Please note down this. When you take average, you should take like this way. Another thing, whether when you calculate Fc stress, P by A or M by Z, do we need to calculate? Do we need to take the dead load or not? Whether dead load also we should consider. The instant answer is no. If you are using, the beam is resting on the pre-stressing bed. Okay, then we don't need to consider dead load. Pre-stressing bed in the sense you know it very well. We will be doing the pre-stressing here one, and this is called pre-stressing bed actually. Okay, this like this, and over this only our beam will be resting. This one, no, here beam will be resting here actually. So if it is resting on the pre-stressing bed, and we will have a pre-stressing bed like this. This is the anchoring abutments. This is our pre-stressing bed like this. So if it is resting on the pre-stressing bed, then we don't need to do. Suppose what happens is after this the beam might bend like this, or it will bend above the table. So at that time we should consider the dead load. Okay, so in this case we need to, if it is resting on the pre-stressing bed. Okay, so that's all with this. So please note down the formula. Loss is equal to M into Fc. This is how we calculate. Yeah. So another one is loss due to friction. So we have seen that see in this case what happens, normally that the pre-stress, in case of pre-stressing, what happens is we will catch the beam first. Let us say this is the anchor abutments. Okay, correct, no? Then we will have a steel like this, correct? steel is stressed, then only we will cast the concrete like this. Yeah. And once the concrete is set, we will cut the steel. Correct? No. So in this case, there is no chance of friction actually, because we don't pull the steel. We initially pull the we won't pull the steel within the concrete actually, right? So there is no chance of friction actually. So this will happen mainly for the post-tensioned beams actually. Pre-tensioning friction will not happen. Yeah, will not consider, even though it is there a little bit, but it's not that much actually, so will not consider. Okay, so in post tensions what happens, this blue color, you can see it is a what you call, it's a duct actually, wherein your tendons are like this. So initially your tendons will not be straight actually, it will be in a curved like this, curly like this. So this is called wobbling effect actually. So friction will not come alone, friction and wobbling effect also we need to consider. So first we need to apply some force, we need to apply some stress, to make it straight actually, right? Then what happens, we will pull it. Okay, so we will pull it, then we will apply the grout and everything. So what happens is there is a friction will also be there between the ducts and the steel actually. Okay, so that will be coming into picture, and for which we need to find out the loss. So loss due to friction is found out like this: P0 minus P0 into E minus mu alpha plus K into X. Let us see, P0 is initial compressive force, initial force, pre-stressing force, and mu is a coefficient of friction between the steel and the material actually. So this is normally it is given in the question 0.25 to 0.55, and alpha is nothing but theta 1 plus theta 2. That is, you can see here, see, if you see here, let us say this is the profile, and let us say this is theta 1 here, this angle where we're in horizontal, the tendon profile makes it the horizontal, this is theta 2. Okay, then theta 1 plus theta 2 is called your what you call your alpha. Remember, it is in radians actually. So approximately you can take, because theta 1, how do you calculate theta 1? This is tan theta is E by L by 2. Okay, theta 2 is also E by L by 2. So if you add it, 8E by L by 2 will come actually. Alright, no? So that is what, that is how it comes. This one. Alpha, theta 1 plus theta 2, we can take it as 8E by L. Alright. Then K is nothing but the wobble coefficient, because since I told you what it is, wobble, it will be coming, the steel will be coming like this. So that is called the wobble coefficient. It is normally it is given in the question 0.0015 to 0.005 per meter length of the tendon, and X is the span. So one thing we should notice is that if sometimes normally we say that the steel will be pulled from both sides. Suppose it is pulled from only one side. Okay, there can be like that also. If it is stressed from one side, then L is equal to L itself, and if it is stressed from both sides, then L should be taken as L by 2. That you please keep in mind. Okay, if stressed from one side, then X should be taken as L. If it is stressed from both sides, then X should be taken as L by 2. Okay, so please note down. So this is how it is calculated. Next is loss due to anchorage slip. This is also mainly it's happening in the post tension, because post tension we pull the steel after the concrete, after the concrete is set actually. So there can be, once it pulled and when the jack is placed, then there is a chance of again it might lose, or it might some slip will happen actually in wedges and everything. So that is called this one, and this is the formula we use it for finding out. This is a simple one: delta E by L. The delta is equal to change in length, how much it is shortened, slipped. Then E is equal to Young's modulus of steel, and L is equal to the span. Yeah. Another thing is loss due to creep. It is a time dependent. So whatever We have discussed now it is immediate losses. Now we are going to discuss time dependent. Time dependent losses are happening for both pre and post tension. Okay, so loss due to creep. So creep, you know that when a load is when a beam is subjected to load for a long time, then there's a chance of it might deflect more. So all this that because of the inertia, this creep happens actually. So loss due to creep is equal to m into theta into fc, where m is modular ratio, which we have discussed, es by ec, Young's modulus of steel divided by Young's modulus of concrete, and theta is equal to creep coefficient. Yeah, and fc, this creep coefficient can be taken from the table, and fc is stress in concrete at the level of steel, which we'll calculate. So theta is, and it's time dependent actually. So theta is taken as 2.2 for 7 days, and 1.6 for 28 days, 1.1 is for 1 year and above. Okay, so another thing I want to emphasize here, it is this theta is, suppose it is asked you to find out 14 days theta, then you cannot interpolate it actually, because it is not linear. So theta is linear with not linear with time, but theta is linear with log t to the base 10. Okay, so with this you can interpolate it actually. Okay, right? So another thing is shrinkage loss. Shrinkage loss is nothing but shrinkage of concrete. The loss happens due to shrinkage of concrete. When concrete gets shrinked over a course of time. So shrinkage loss is equal to ES, Young's modulus of steel, into the shrinkage strain. Shrinkage strain is 0.003 into 3 for pretension, and 0.0002 by log 10 log t plus 12 to the base 10, which is for pretension. And no case, this 0.002 by log t plus 2 to the base 10 should be more than 0.003. The maximum value of this one should be 0.003. Yeah, another thing, the last one in this case is loss due to stress in relaxation. This meaning is that, for example, you have done a pre-stressing, a steel is pre-stressed and concrete is cast, and let us say today, and after say some 10 years or 15 years you come back and check the stress in the steel, then that stress will be less than, so there will be automatically a loss might have happened of a course of time, the stress in steel relaxation. So losses are it is shown in the table. So if your pre-stressing force is 0.5 fp, fp is proof stress. If it is 0.5 fp, then there is no loss. If it's 0.6 fp, it is 35 megapascal, and 0.7 fp, it is 70 megapascal, and maximum, we will apply the stress, it's maximum to 0.8 fp. Proof stress is nothing but it is like this. Proof stress is nothing but, if it is a stress strain curve, if I draw, and let us say this is your what do you call 9, for 0.2 percentage, let us say this is 0.2 percentage here 0.2 percentage. Then if I draw a dotted line like this, yes, so that will meet here, that this is stress, that is called the proof stress. Okay, so that is 80%. Maximum we will take only 0.8 fp, only the maximum pre-stressing force. If that is the case, 90 MPa is a loss actually. So this is the summary of that. Immediate stress, elastic shortening, it is happening in the pre-stress. Post tension, it will not happen if all the wires are stressed at the same time. If you are stressing it one by one, then this will happen. When you do a problem, you will understand. Friction and wobble losses, it is for post tension only. So this is the formula. Anchorage slip, it is for post tension. This is the formula. Creep is also for both pre and post. Time dependent is for both. Okay, so hope it is clear. When we do a problem, you will understand.